Swayam Prabha. Digital India. Educated India.
I welcome you to this lecture of flow through porous media. We were discussing about this miscible displacement. In particular, we talked about this process of dispersion of solute of tracer in porous media. What we had been talking about is as the flow takes place in a porous media, how mixing takes place, and particularly for in the last lecture we talked about the step change in concentration. If one gives a step change in concentration, how this step change evolves at the outlet. I mean, step change in concentration, how the concentration profile evolves at the outlet. And by looking at that concentration profile, what I mean, how with some amount of finesse, how we can characterize the porous media, or which porous medium is giving more mixing, which one is giving less mixing. So instead of looking at the experimental data, we try to put together these certain theories, and we talked about these dispersion coefficient or Peclet number or the dimensionless time, and those kind of terms we could arrive at. So in this regard, I must point out that since we are discussing about these this flow through porous medium, when there is a porous medium, we said that there could be a stagnant, at the end of last lecture, if you recall, we were talking about a stagnant zone. So what could be the effect of a stagnant zone? So in this regard, let us see if what would be the case if there is a hypermeability streak or a so called fracture, that means a crack exists inside a porous medium. Let us say a fracture runs through this porous medium. So let us say a fracture runs through this porous medium, and what you have given is a step change in concentration, and you are trying to plot the concentration at the outlet. You are writing it as C bar by C 0 as a function of, I am writing it as PVs, number of pore volumes. Had it been just a uniform core without any fracture, I would have observed around one pore volume there would be a breakthrough. So this is called breakthrough. Okay. This point is where first concentration is registered at the outlet. So this is the breakthrough point, and then at some point the concentration is reaching 0.5. Okay. Concentration is reaching 0.5. So this is 0.5 and this is 1.0. So at the end it would be reaching 1.0. So if there is no fracture, if we assume that there is no fracture, then we would have expected a plot something like this, and we could have said that now let us see, we call this to be 1 pore volume, 1 PV. Okay. Why we are calling this to be 1 PV? Because you recall this form equation that we arrived at for the step change. It was C bar by C 0 is equal to half into 1 minus error function of Z minus U bar T divided by I believe it is square root of 4 dt or 4 dCTD. Okay. So, if this is the concentration profile, so then when we try to apply this for a porous medium, first of all I must point out that this u bar has to be equal to interstitial velocity, not superficial. U bar has to be interstitial velocity, because we are extending now, instead of a capillary we are calling it the porous medium. So, instead, in case of a porous medium, this velocity was applicable for velocity through the capillary, and porous medium we have considered porous medium as bundle of capillary. So, the velocity inside the capillary we are talking about, not overall velocity. Okay. So, this u bar is interstitial velocity. This we must remember. Okay. So, when t is equal to residence time, when t is when t is equal to t res, that means when t is equal to the residence time, then what would be u bar into residence time in this case? Think of a capillary. Think of a capillary. I have this velocity is, let us say, u bar, and residence time it takes is supposed to take is t res. Okay. So, then in that case, what would be the u bar divided by t res, or just one second, what would be the u bar multiplied by t res? What does this give? First of all, unit wise I can see u bar is meter per second and t res is second. So, meter per second into second, they will cancel out. So, this has a unit of meter. If you look at it, u bar is the time, u bar is the velocity, that means the distance this fluid front travels, the center point of the fluid pond, or in an average sense the distance the fluid front travels over time of 1 second. Let us say if u bar is so and so meter per second. So many meter will be travelled in 1 second. So, over t res, that residence time, u bar into t res is that this is the length this midpoint of this fluid front will travel. So, that means the midpoint of the fluid front would travel. So, this u bar into t res is the length scale. So, that means after t res time, the midpoint of the fluid front would travel from this end to that end. That is the idea, right. So, then this u bar into t, then when t is equal to t res, u bar into t becomes equal to L, where L is the length of the capillary, or in this case length of the porous medium. So, here what are we plotting, by the way? We are plotting the concentration C bar at outlet, frankly speaking, at outlet. So, C bar at outlet we are plotting divided by C 0. So, at outlet we are plotting means this Z will be simply equal to the length we are plotting, right, because we are interested in not any ZT, anywhere we are not interested, though we can find out using these equations, but we are not doing that. For a porous medium, I have very little, I mean generally it will be easier for me to collect the sample from the outlet and measure its concentration. So, naturally this C bar would be then as a function of LT we are looking at, not ZT. So, automatically this, instead of Z, now we will have L. So, now we will have L, and we said that this at t is equal to t res, u bar t is equal to L. So, what that means is when C bar L we said, so basically it is when we are finding out C bar at L and t res at residence time at the outlet when we are trying to find out, then that would be equal to half into 1 minus this quantity, but then u bar t is equal to L. So, that means L minus u bar t, this whole term becomes equal to 0, and ER of 0, we remember I have already talked about these ERF function x versus ERF, this is x, this is ERF of x. So, we know that it is going to be 1.0 it goes, but at x equal to 0 it would be 0. So, that means this whole error function term is becoming 0 when we are talking about z as equal to L and time is equal to t race, that means the residence time. So, then this, if this term is equal to 0, then this becomes equal to, this whole thing is becoming equal to half into 1 minus 0, which is 0.5. So, what essentially it means is that after I injected 1 pore volume, that is what is the definition of 1 pore volume, right? The residence time, the flow that has taken place till the residence time, that is equal to 1 pore volume. If we multiply simply these length multiplied by the area and multiplied by the porosity, this gives me the pore volume. Okay. So, here what that means is, so what I mean to say is that if I had plotted instead of pore volume, if I had plotted these as time, then this 1 pore volume, then this 1 pore volume would have been synonymous to 1 residence time, right. So, it is synonymous to 1 residence time. So, it is the same thing, if it on time scale residence time, on a volume scale 1 pore volume. So, for 1 residence time at Z, this is at the outlet only, for 1 residence time it should have been 0.5, that is what it says, and that is what we see, that it is 0.5. Okay. So, this is, so this makes, so I mean if we, by doing this, I mean we get some better handle over this whole episode, that this C bar by C 0 essentially, though this is the equation we said C bar at Z and T, but essentially when we are plotting this for a porous medium, we are plotting this for C bar at the outlet when we make this plot, and then we said that at this is the time when first time the concentration starts recording, because it would be little less than 1 pore volume because of this dispersion, and then however the midpoint of this curve will always, this should correspond to 1 pore volume, residence time and 0.5 concentration. So, this is intuitively understood, and then it will go rise, it will be reaching 1.0. Now, in this whole show, if you have a fracture running through this, fracture means a crack through which a flow can take place. I mean to say, suppose I have a core, or I have, let us say, a block, let us say this is the block running like this, and in this block there is a crack which is running. Of course, the dimension of the crack is very small, in the of the order of say half millimeter. So, it is, we are talking about 500 micrometer, whereas when it comes to the pore size, we are talking about 1 micrometer to 3 micrometer. Or so it is, so compared to the pore size, this dimension aperture is large, but for our purposes, for the purposes that we are looking at, less than a millimeter is definitely very small aperture. So, now if one fracture runs like this, so naturally the fluid will have a tendency to flow through this, because it is getting a much higher permeability through these crack, through these fracture, rather than flowing through this porous medium. So, what one would see in this case is a very fast breakthrough. Breakthrough means this is breakthrough, that this is here the concentration started rising. So, in this case one would see the concentration rising and rising at here. concentration will start rising from here. So, concentration will start rising from here, and then the concentration. So, there is flow taking place through these channel, and the concentration is the front that I have injected. This will start appearing at the outlet very soon. Only this part of the cross section has to be filled. Only this crack or this part is to be filled, and this volume of this crack is much smaller compared to the total pore volume of this body. Had it been a uniform flow through the, I mean uniform in the sense the uniform sweeping of the resident fluid, we would have expected that entire fluid of this porous medium has to be displaced. So, then only the concentration front can arrive. Out of that understanding, we have multiplied u bar with T res, or we talked about this point u bar T is equal to L and arrive at this 0.5. But if there is a fracture running, so naturally the fluid will be traveling very fast, and of course, this particular volume in fact is in a way this particular volume is an indication what is the volume of this crack. Okay, so this volume of the crack is small, so this is the time, and then it starts breaking through. But after it starts breaking through, then it sort of, this is called a tailing of the profile. So, this is tailing, and it will take a long time to reach the 1.0 value. This whole thing will take a very long time to reach the 1.0 value, because this fluid that is traveling through this cross section, this fluid would what do we have in the surrounding space? This is the surrounding, this is the adjoining space, right? Adjoining space is the porous medium, and this porous medium is having a concentration, let us say 0. Concentration is 0, and this C0 front is traveling through this very fast. So, when it travels through this very fast, there would be diffusion of these, not flow. It is just diffusion. It is something like I am having a flow of a fluid, and flow. I mean I am putting a jet inside a tank. So, tank is filled with certain fluid, and then I am introducing a jet. Jet is moving at a very high velocity. So, but as it goes through the tank, the jet is mixing with the fluid already inside the tank, and still it is reaching the outlet, and I am collecting it from the other side. I will find that the one that I am injecting, that will definitely be much diluted. So, that same effect. So, here also there would be diffusion taking place. So, this concentration would be diluted. So, it would be appearing very fast, but then it turns, and probably it will reach some value of 0.6 or so, and then beyond that it starts tailing, and you have to inject a lot of volume to reach this 1.0, which is much higher than the pore volume, because this, so flow will continuously predominantly will take place through this. Okay. There could be some flow which will take place through this adjoining medium also. In fact, that depends on the permeability ratio. This aperture, it will have some permeability. This permeability would be, let us say we have as I said, the aperture is B, then if you have, then permeability would be given by B square by 12, one can find out. It would be of the order of 1000 of Darcy, whereas this is of the order of milli Darcy. So, then this is, so there could be a permeability contrast. So, depending on this permeability ratio and the area ratio, so some flow will take place. Always there would be some minimal flow that will take place through this side very slowly. Okay. But main flow would be through these crack, and then as it travels, as the solute travels through this solute will continuously be diffusing into the adjoining medium, adjoining pore space, which is filled with liquid of 0 concentration. So, that is why, because of this diffusion, there would be dilution of the front. So, it would be much less than 1.0, and one has to continue to flow. Whatever you are injecting, the flow will immediately take place through this channel, but this entire thing has to be fed. Entire concentration has to be changed by diffusion. and that would take long time. It is the same situation what I discussed in a previous lecture as stagnant zone, a very similar situation. This part of the fluid is not, you are not letting this part of the fluid to flow. Instead, you are slowly feeding to this part of the fluid with the solute, but that is only by diffusion. So, this flow will take place very fast, but because of this diffusion it will take a long time to reach C by C0. So, these are some of the aspects we must make note of as we are gradually making the transition from dispersion in a capillary to dispersion in a porous medium. Now, dispersion, we said that if you recall, if we have one dimensional flow, and then we have talked about this dispersion, if they, I mean one can think in this line, and this is common in case of a porous medium, to put this as longitudinal dispersion, DL, longitudinal dispersion, that means dispersion that will take place in the longitudinal direction. Okay. So, in fact there is a I mean when there is a flow taking place, we can consider this dispersion to be longitudinal and transverse, but let us focus on only longitudinal dispersion, because that is what we have studied in Taylor dispersion, or that is what we have studied so far. So, what I am trying to say is that this is not diffusion anymore, this is dispersion, So, this term we are using now as dispersion. So, what we had in Fick's second law, we have been talking about all the time, del square C del T is equal, del C del T is equal to diffusivity multiplied by del square C del x square type term. But here in this case, so this when we arrived at this, what did we do? We had picked up a differential element, and then in minus out is accumulation, and we arrived at this del C del T is equal to diffusion coefficient multiplied by del square C del x square if this direction is x. So, this is concentration. So, here we have directly we are saying that okay, there is a flow taking place. So, this is not going to be a diffusion. So, let us directly put this as dispersion coefficient. That means this accounts for both diffusion and the effect of velocity, and because of that there is smearing of the front, and so all those are included. So, instead of diffusion coefficient, now we are talking about dispersion coefficient, and so with that is given the name L, and since we are looking at dispersion in this direction, this we are calling longitudinal dispersion. Further, we have this term, you might have noticed already when we defined a Taylor dispersion, that there would always be some component of convective, term has to be there. That means, I pick up a differential element, I pick up a differential element perpendicular to the screen area A. So, what I know that if this is A, then we are always putting some VDF is the interstitial velocity in this case. So, V some velocity which is entering, and this has some cross sectional area over which. So, this is the volumetric flow rate multiplied by the concentration at x, and here we have same VAC at x plus delta x, and so we can take the difference between the two, and when we write this write the mass continuity, that means when writing the Fick's second law, if when we arrived at Fick's second law, we considered only diffusion. That means, at the inlet the flux is minus d del C del x at x, and here it is minus d del C del x at x plus delta x, and the difference is accumulation. So, that is we are considering only diffusion at that time. If we have on top of this diffusion, if we have some flow taking place, and because of this flow something is being carried to this differential element, by this volumetric flow rate and something is leaving from the other side. So, if we take that balance, that means this difference if we take, and then if we take when we divide by delta x, that means the way we had divided by delta x and set limit delta x tending to 0, when we do that exercise of limit delta x tending to 0 and then VAC at x minus VAC at x plus delta x divided by delta x, when we do this and we take V outside as a constant, then we end up with minus V df del C del x. Here we have a minus sign because in this case we started with a minus sign, but here we do not start with a minus sign. Here this minus sign got cancelled out, so that is why we have this term, but here this minus sign, there is no minus sign. So, here there would be a minus sign. So, this is called a convective term. Now, what we are saying is, suppose there is a chemical reaction. So, if there is a chemical reaction, then one must consider another reaction term. That means, within this volume, if there is a reaction taking place. So, within this volume, since it is I am writing it as plus, so RCT is the rate of production of solute per unit volume of solution. So, now and VDF, mind it, when we are applying this to a porous medium, VDF has to be the interstitial velocity. So, what that means is that this becomes the governing equation when somebody has a reaction happening inside the porous medium. If it is only flow taking place, so when there is a flow plus diffusion taking place, Taylor dispersion was about a capillary. Okay. Taylor dispersion was the Taylor dispersion, there also we worked with del C del T term, and there we had a radial diffusion and there was axial convection. But now, if we when we are talking about porous medium, we have taken that experience, we have taken that wisdom, all those informations are with us. But now what we are doing is, if we for the time being, let us say if we leave out this reaction term, we are considering this part. That means, this is the accumulation term, this is the diffusion, but not exactly, D is not the diffusion, we are directly putting dispersion coefficient, and this is the convection, that means the solute that is carried because of the velocity term. So, these are one has to work with this interplay. So, this is, and mind it, this VDF is now considered interstitial velocity. So, now we are no longer in capillary, no longer in a channel, we are directly into porous medium. This V has been replaced as V is now VDF, it is the interstitial velocity. This D is not diffusion coefficient, D is dispersion coefficient. So, it takes into account all aspects, that there would be mixing inside the porous medium and what one should have. So, now this would be the equation that is governing, and on top of that you have, when there is reaction, on top of that you have this reaction term. So, this is the expression that one must follow if there is simultaneously a flow, a reaction, a reactive flow inside the porous medium. There is some mixing taking place because of this flow as well as diffusion process, and then there is some reaction happening. So, you can see we have taken all these wisdom that we had from the processes in capillary, and then gradually did the transition, and now we are talking about this entire process as for porous medium. And now this dispersion coefficient that we talked about, now this dispersion coefficient you can define. If you have some idea of what is the radius of the pore, you can go by r square d plus r square v square by 48 d, or simply r square v square by 48 d. One needs to have the understanding of what is r and what is the diffusion, true diffusion, bulk diffusion coefficient. So, those informations are required, or if you have some experimental data, one can fit for that same porous medium and can find out what is the dispersion coefficient by following that plot and fitting through that through the data points through the equations that we discussed so far. So, I want to stop here at this point. I will continue this discussion of dispersion in the next lecture, particularly we would look at what kind of knowledge we have with regard to this dispersion in porous medium, what kind of experimental data people have gathered so far. They have taken various samples of porous medium, they have conducted these experiments that I mentioned just now with step change and everything, and they found out what are the dispersion values they got depending on what are the grain sizes and all those things. So we will touch upon those in the next lecture. So that is all I have for this lecture. Thank you very much.